let's get right into it. Welcome to a journey into the top 20 most venomous creatures on Earth. As we traverse the globe and delve deep into the mysteries of nature's most lethal guardians. These beings, equipped with some of the most complex and mysterious biochemical arsenals known to science, may seem like agents of death. But could there be more to their venomous capabilities than meets the eye? From the vastness of the ocean's abyss to the secluded nooks of rainforests and the stark landscapes of deserts, these creatures thrive. Their venom, a substance so powerful it can alter the very fabric of life. But is it merely a tool for survival, or is there a greater purpose? Could these potent venoms hold the keys to understanding not only life's evolutionary mastery, but perhaps even the secrets of ancient medicines once believed to be lost to time? Across the globe, in the most secluded and mysterious regions, coming in at number 20, the King Cobra holds dominion with its formidable venom. This creature, more than just a predator, may be a guardian of profound, ancient secrets. As we delve into the mysteries of the King Cobra's venom, we explore not only its deadly capabilities, but also the deeper implications of its evolutionary design. Could there be a link between this venom and ancient knowledge far beyond our current understanding? The King Cobra's venom is a meticulously crafted blend of neurotoxins, cardiotoxins, and various enzymes, each serving a specific and deadly purpose. The neurotoxins, primarily alpha neurotoxins, hijack the victim's nervous system, mimicking and blocking neurotransmitters at the neuromuscular junctions, leading to immediate paralysis. The cardiotoxins complement this by attacking the cardiac cells, potentially causing fatal arrhythmias. These components are delivered in a venom dose sufficient to kill 20 humans or even an elephant, hinting at a power that could be seen as both a natural evolution and a phenomenally precise biochemical weapon. Is it possible that this venom has roots in an ancient bioengineering knowledge? When the King Cobra strikes, it can deliver multiple bites in a single encounter, each injecting venom deep into the tissues of its prey or aggressor. This method ensures that the venom spreads quickly, overwhelming the body's natural defenses. The neurotoxins begin their work within minutes, paralyzing the victim and leading to respiratory failure if untreated. The rapidity with which the venom acts is both awe-inspiring and terrifying. It raises questions about whether this mechanism is purely natural or if it could be the product of an ancient intelligence, perhaps guiding the evolution of such creatures on Earth for reasons we can only speculate about. The effect of the King Cobra's venom on humans is severe and swift. Initial symptoms can appear within minutes, starting with localized pain and swelling at the bite site, followed by a progression to blurred vision, difficulty swallowing, and severe abdominal pain. Paralysis and respiratory failure can occur shortly thereafter, leading to death if antivenom is not administered promptly. The only effective treatment is the immediate application of antivenom, which must be given as soon as possible after the bite to counteract the toxins. Recovery depends heavily on the amount of venom injected and the quickness of receiving medical care. Survivors often require extensive supportive care to manage the systemic effects of the venom. The venom of the King Cobra is not merely a tool for survival, but potentially a link to ancient, advanced biological knowledge. Its rapid effects on victims and the intricate composition of its venom suggest a sophistication that may surpass simple, natural selection. As we explore the depths of this venom's capabilities, we must consider both the scientific and mystical implications. The King Cobra's existence challenges us to think about the origins of life's complexities, perhaps influenced by ancient forces that watched over the early development of life on our planet. Flying in at number 19, the Asian giant hornet, Vespa mandarinia, is renowned not only for its imposing size, but also for its extraordinarily potent venom. This venom is a sophisticated biochemical tool that serves as both a weapon for predation and a shield against threats. At the molecular level, the venom of the Asian giant hornet is a complex mixture of pharmacologically active peptides, enzymes, and amines that collectively induce pain, inflammation, and tissue damage. The primary components include neurotoxin, a peptide that is highly cytolytic, meaning it can rupture and destroy red blood cells and other tissue cells by disrupting cellular membranes. This not only causes immediate tissue damage, but also contributes to the pain and swelling experienced after a sting. Phospholipase A, an enzyme that plays a critical role in the venom's ability to cause pain and inflammation. It acts by breaking down phospholipids in cell membranes, leading to increased membrane permeability and subsequent cell death. Hyaluronidase, often referred to as the spreading factor. This enzyme facilitates the rapid diffusion of the venom through the victim's tissues by breaking down hyaluronic acid, a major component of the extracellular matrix. Acetylcholine, an unusual component for venom, this neurotransmitter significantly enhances the pain response by prolonging the action of nerve signals at the synaptic junctions. The venom's primary action is cytotoxic and hemolytic, targeting cell membranes and leading to lysis, rupture, of both blood and tissue cells. The phospholipase A in the venom catalyzes the hydrolysis of phospholipids, forming lysolecithin, a compound that disrupts cell membranes and enhances the permeability, leading to cellular breakdown. The systemic effects of the venom, particularly when delivered in multiple stings, can be severe. The rapid destruction of cells releases a large quantity of cellular debris into the bloodstream, which can trigger an overwhelming immune response, potentially leading to anaphylactic shock, a severe allergic reaction that can be fatal if not treated immediately. The impact on humans stung by the Asian giant hornet can range from transient pain and swelling to severe systemic reactions. The pain, described as throbbing and unrelenting, is primarily due to the action of neurotoxin and acetylcholine, which directly stimulate nerve endings. Swelling and redness are due to the inflammatory response incited by the venom's enzymes. In cases of multiple stings or in individuals who are allergic to the venom's components, the reaction can escalate to severe anaphylaxis, characterized by difficulty breathing, a drop in blood pressure, dizziness, and a rapid pulse. Immediate medical treatment with epinephrine is required to counteract these symptoms. The venom of the Asian giant hornet has piqued the interest of the medical and scientific community due to its unique properties. Researchers are particularly interested in the potential anti-cancer properties of neurotoxin and phospholipase AA. These components, due to their ability to selectively break down cell membranes, are being studied for their potential to target and kill cancer cells without harming healthy tissue. Slithering through at number 18, the inland taipan, often heralded as the world's most venomous snake, possesses a venom that is both fascinating and fearsome in its efficiency. Known scientifically as Oxyuranus microlepidotus, this serpent's venom contains an array of toxins that have evolved to target specific physiological systems with devastating precision. The venom of the inland taipan is a finely tuned mixture of neurotoxins, procoagulants, myotoxins, and cytotoxins, each playing a role in incapacitating its prey. Neurotoxins, taipoxin, and tetrodotoxin. These are the most potent components of the venom, disrupting the nervous system by blocking neurotransmitters, which can lead to paralysis and respiratory failure. Procoagulants. These toxins affect the blood's ability to clot, causing the victim to suffer from disseminated intravascular coagulation, DIC, where blood clots form throughout the body, leading to severe bleeding and organ damage. Myotoxins. These toxins cause muscle damage, enhancing the overall debilitating effect of the venom and contributing to systemic collapse. Cytotoxins. They cause cell death and tissue damage at the site of the bite and in surrounding tissues, exacerbating the injury and preventing the wound from healing. Upon injection, the venom's neurotoxins rapidly spread through the victim's body, targeting the neuromuscular junctions. Here, they bind to the acetylcholine receptors, blocking nerve impulses from triggering muscle contractions. This blockade results in flaccid paralysis, preventing normal breathing and leading to suffocation if untreated. The procoagulants in the venom trigger an abnormal activation of the clotting cascade, leading to the formation of microclots throughout the bloodstream. This not only depletes the body's clotting factors, leading to uncontrolled bleeding, but also causes blockages in blood vessels, impairing blood flow and leading to organ failure. The effects of inland taipan venom on humans are acute and can escalate quickly if left untreated. Initial symptoms include headache, nausea, abdominal pain, and vomiting, which can rapidly progress to more severe conditions such as muscle weakness, renal failure, convulsions, and internal bleeding. Due to the high potency of the neurotoxins and procoagulants, the venom can be fatal within hours without antivenom treatment. The extreme potency of the inland taipan's venom makes it a subject of intense interest in toxinology and pharmacology. Researchers study the specific actions of its toxins to develop more effective antivenoms and to explore potential therapeutic uses. For example, neurotoxins from the venom are studied for their potential in neuromodulation therapies for diseases involving overactive nerves. The procoagulant properties of the venom are researched for insights into the blood clotting process, which could lead to new treatments for clotting disorders. The specific enzymes involved in these processes could also offer templates for new drugs that could finally control clotting in surgical or trauma settings. A silent killer of the sea floating in at number 17. The blue-ringed octopus, a marvel of the marine world, is as beautiful as it is deadly. Small in size yet formidable in defense, this creature carries a venom that contains one of the most potent neurotoxins known to science, tetrodotoxin. The venom of the blue-ringed octopus works by binding to the sodium channels of nerve cells, effectively blocking the passage of sodium ions into the neuron. This inhibition prevents the nerve cells from depolarizing, halting the propagation of nerve impulses. Without the ability to transmit signals, muscles receive no commands to contract, leading to paralysis. This mechanism primarily affects the muscles involved in breathing, posing a fatal risk through respiratory failure. The venom of the blue-ringed octopus is primarily composed of tetrodotoxin, TTX, a powerful neurotoxin that blocks sodium channels on nerve cells, preventing the transmission of nerve impulses and leading to paralysis. Alongside TTX, the venom also includes smaller concentrations of dopamine and serotonin, which can modify the pain and inflammatory responses, respectively, though their roles are not as critical as TTX in the context of venom action. Tetrodotoxin, TTX. This is the primary component that is responsible for the venom's deadly reputation. TTX is highly specific to sodium channels in nerve cells, making it an extremely effective blocker of neuromuscular transmission. Dopamine and serotonin. These compounds may help modulate the victim's physiological response to the venom, potentially exacerbating the effects of TTX by altering blood flow and pain perception. The effects of blue-ringed octopus venom on humans can be swift and severe. Symptoms usually begin with numbness around the bite area, followed by a gradual onset of nausea and an increasing sense of weakness. As the TTX spreads, it leads to progressive, flaccid paralysis. Critical symptoms that can develop include difficulty swallowing, speaking, and breathing. In severe cases, the victim may experience respiratory arrest and cardiovascular collapse. Without immediate medical intervention, primarily supportive care, including artificial ventilation, the paralysis can be fatal, as there is currently no antivenom available for TTX. The distinct action of tetrodotoxin on sodium channels has made it a valuable tool in neurological research. Scientists study TTX to better understand the functioning of nerve cells and the transmission of nerve signals, which is fundamental in diseases that affect neuromuscular functions, such as multiple sclerosis and amyotrophic lateral sclerosis. Furthermore, because TTX blocks pain signals without causing sedation or addiction, researchers are investigating its potential as a novel painkiller that could serve as an alternative to opioids. This aspect of TTX research holds significant promise, offering a potential pathway to pain management solutions that avoid the pitfalls of current opioid-based medications. Lurking in the oceans at number 16. The venom of the box jellyfish is of significant interest to the medical and scientific community due to its unique properties. Researchers are particularly focused on understanding the specific pathways through which the venom operates, which could lead to breakthroughs in cardiovascular and neural pharmacology. Insights gained from studying the venom's action on cells and tissues are informing the development of new drugs for managing cardiac arrhythmias and acute pain. The venom's efficacy in targeting and rapidly incapacitating prey has potential implications for developing faster-acting medicines. The box jellyfish, known scientifically as Chironex fleckeri, operates through a sophisticated array of toxins that target the heart, nervous system, and skin cells. It includes a suite of potent proteins and peptides, such as porins, that form pores in the membranes of nerve and muscle cells, leading to rapid ion imbalance and cell death. This action disrupts the cardiac and neuromuscular systems almost instantly, causing extreme pain, paralysis, and, in severe cases, heart failure. These mechanisms make the venom incredibly effective at quickly incapacitating its prey and deterring predators. One of the most feared creatures of the tropical seas is the box jellyfish, whose venom stands among the most deadly in the natural world. The venom of the box jellyfish is a complex cocktail of proteins, including cardiotoxins and neurotoxins, that are among the most potent found in the animal kingdom. These toxins are capable of attacking the heart, nervous system, and skin cells, leading to a rapid and often fatal outcome. The venom's primary components are designed to immobilize prey and deter predators, showcasing an evolved biochemical strategy for survival. Cardiotoxins disrupt the normal rhythm of the heart, leading to cardiovascular collapse. Neurotoxins interfere with nerve transmission, causing severe pain, paralysis, and potentially death. Dermonecrotic toxins destroy skin tissues and induce severe inflammation and pain at the contact site. The impact of a box jellyfish sting on humans can be catastrophic and immediate. Victims often experience overwhelming pain, and the venom can swiftly lead to systemic reactions. Symptoms typically include intense pain at the sting site, followed by nausea, vomiting, and an increase in heart rate. More severe stings can result in muscle cramps, acute renal failure, cardiac arrhythmias, and even death within a few minutes if the exposure is extensive. Immediate treatment with vinegar to inhibit further nematocyst discharge, and rapid medical intervention are crucial to manage the symptoms and prevent a fatal outcome. With 8 limbs, there isn't one single reason to touch this creature, coming in at number 15. The venom of the Sydney funnel web spider, a complex concoction of neurotoxins, affects the nervous system with terrifying efficiency. The primary component, D-hexatoxin, targets the ion channels responsible for nerve signal transmission. By modifying the gating dynamics of sodium channels, the venom prolongs their activation, causing continuous nerve firing. This results in severe pain, muscle spasms, and can lead to systemic symptoms like respiratory distress if the venom spreads extensively. Renowned for its potency and rapid effects, the venom of the Sydney funnel web spider is among the most studied in the world. When humans are bitten by the Sydney funnel web spider, the onset of symptoms can be rapid and intense. Initially, the bite site may appear minor, but within minutes, the victim may experience severe pain, muscle spasms, and sweating. As the venom continues to circulate, systemic effects can include tachycardia, hypertension, and in severe cases, neurological complications such as confusion or coma. The severity of the reaction can vary based on the amount of venom injected and the individual's susceptibility. The venom of the Sydney funnel web spider is particularly rich in neurotoxins that are designed to quickly incapacitate prey. Key among these toxins is hexatoxin, which specifically targets the nervous system. The venom also contains an ensemble of enzymes that facilitate the spread and increase the efficacy of the toxic components, maximizing the impact on the prey or predator. This biochemical arsenal makes the Sydney funnel web spider one of the most feared arachnids in Australia. The neurotoxic components of the Sydney funnel web spider's venom have become a focus of neurological research. The specific action of hexatoxin on sodium channels offers valuable insights into the development of drugs aimed at managing chronic pain and other neurological disorders. Additionally, understanding how these toxins affect nerve cell functioning could lead to breakthroughs in treating or managing conditions characterized by nerve hyperactivity or dysfunction. In the arid landscapes where the earth bakes under the relentless sun at number 14, the Gila Monster moves with a deliberate grace that belies its dangerous nature. This lizard, one of the few venomous species known to man, carries within its glands a venom that has piqued the interest of scientists and scholars alike. The venom of the Gila Monster is a complex biochemical brew, primarily composed of proteins and peptides that modulate the prey's body functions to facilitate easier subjugation. Among these proteins, exendin-4 stands out for its similarity to a human hormone involved in regulating blood sugar levels. This component not only causes hyperglycemia in the Gila Monster's prey, but also offers intriguing implications for diabetes treatment in humans. Additionally, the venom contains hyaluronidase, an enzyme that promotes the spread of venom by breaking down cellular barriers, and phospholipase A2, which disrupts the victim's cell membranes, further aiding in the immobilization and digestion process. When the Gila Monster bites, its venom flows through grooved teeth, a method of delivery quite distinct from the hypodermic injections seen in snakes. The venom's action is primarily to stun and disorient the prey, facilitating easier handling and ingestion. The toxins achieve this by interfering with nerve transmission and causing muscle weakness and pain, which can be severe and debilitating. While not typically fatal, the effects of a Gila Monster bite on humans can be quite severe. The immediate symptoms include excruciating pain at the bite site, edema, and sometimes a drop in blood pressure. The pain can spread and persist, leading to nausea and general malaise. Despite these potent effects, fatalities are rare, largely due to the slow metabolism of the Gila Monster, which limits the amount of venom it can inject in a single bite. The real intrigue of the Gila Monster's venom lies in its potential for diabetes treatment. Exendin 4, a peptide found in the venom, has been synthetically developed into a drug called exenatide, Byetta, which is used to enhance insulin secretion and regulate blood sugar levels in type 2 diabetes patients. This is a prime example of how venom, often feared and avoided, can be repurposed to benefit human health in significant ways. Ongoing research into the venom's components like hyaluronidase and phospholipase, A2 is opening new pathways for understanding how to treat chronic pain and inflammatory conditions, potentially leading to more effective and targeted therapies. Deep within the savannas and dense forests of Africa at number 13, the Tsetse Fly, a creature often overlooked, carries a venom with profound biological implications. Explore the complex venom of the Tsetse Fly, which, unlike many venomous species, acts as a vector for a parasite that causes sleeping sickness, a disease that has plagued humans and animals alike. The focus here is to delve into the venom's role, its effects, and the potential it holds for understanding ancient pathogens and modern medical challenges. While the Tsetse Fly does not produce venom in the traditional sense, it is the sole biological vector of the trypanosomes that cause African trypanosomiasis in humans and animals. The saliva of the Tsetse Fly contains various compounds that facilitate the transmission of these parasites. These include anticoagulants that prevent the host's blood from clotting during feeding, as well as immunomodulatory proteins that suppress the host immune response, allowing the parasites to survive and multiply within the host. The Tsetse Fly's feeding process is intricately tied to the transmission of trypanosomes. When it bites a host, its saliva, laden with parasites and biochemical modulators, is injected into the bloodstream. The anticoagulants ensure a steady flow of blood, while the immunomodulatory proteins modulate the host's immune defenses, enabling the parasites to evade detection and destruction. Once inside the host, the trypanosomes undergo several developmental changes as they adapt to their new environment, eventually invading various bodily tissues, including the blood, lymph, and central nervous system. The impact of the Tsetse Fly's bite can be devastating. African trypanosomiasis, or sleeping sickness, begins with simple, often overlooked symptoms such as fever, headaches, and joint pains. As the disease progresses, neurological symptoms develop, including changes in behavior, confusion, sensory disturbances, and poor coordination. In the disease's later stages, severe sleep disturbances occur, giving the illness its name. Without treatment, the disease is typically fatal, with the parasites causing extensive neurological damage. The study of Tsetse Fly saliva and its role in trypanosome transmission is of great interest to researchers seeking to understand and control sleeping sickness. The biochemical properties of the saliva, including its anticoagulant and immunomodulatory capabilities, offer potential targets for new treatments or preventive strategies against trypanosomiasis. For example, disrupting the action of these compounds could reduce the efficiency of parasite transmission, providing a new approach to disease control. Understanding how trypanosomes evade the immune system can provide broader insights into immune system function and potential weaknesses that could be relevant for other diseases, both infectious and autoimmune. In the mysterious depths of the ocean, at number 12, the Cone Snail glides silently, bearing a venom complex enough to paralyze and capture its prey with precision. Known for its beautifully patterned shell, this creature conceals a potent biochemical arsenal, making it one of the most fascinating subjects of marine toxinology. The venom of the cone snail is a sophisticated concoction of hundreds of peptides, known collectively as conotoxins. These peptides are highly specialized, each targeting specific ion channels and receptors within the nervous system of its prey. The diversity of conotoxins found in a single cone snail species can be vast, suggesting a complex evolutionary history geared towards optimal predatory efficacy and defense mechanisms. Voltage-gated ion channel blockers. These conotoxins interfere with the normal function of nerve cells by blocking the ion channels that are crucial for nerve signal transmission. Neurotransmitter release blockers. Other peptides in the venom inhibit the release of neurotransmitters, preventing nerve signals from passing across synapses. Pain-inducing peptides. Some conotoxins directly induce pain, which can disorient the prey and deter potential predators. The cone snail uses a harpoon-like radula tooth to inject its venom into prey, a method as effective as it is swift. Once the conotoxins enter the bloodstream of the victim, they quickly bind to their specific targets, disrupting normal neurological and muscular functions. This can lead to paralysis within moments, illustrating the venom's potency and the precision with which cone snails have harnessed their chemical tools. Although interactions between humans and cone snails are rare, the effects of a cone snail sting can be severe due to the potency of the venom. Victims may experience intense, localized pain, followed by numbness and tingling sensations. More severe stings can lead to muscle paralysis, respiratory failure, and in some cases, death if not treated promptly. The lack of an antivenom adds to the danger, making supportive care the only current treatment option. The venom of the cone snail has captivated researchers due to its precision and potency, offering promising avenues for drug development. Conotoxins have been studied for their potential use in pain management, with certain peptides showing the ability to provide pain relief significantly more potent and specific than morphine, but without the addictive side effects. Additionally, the ability of certain conotoxins to specifically target neuronal pathways is being researched for the treatment of neurological disorders such as Alzheimer's and Parkinson's disease. At number 11, hidden within the depths of the ocean, the pufferfish holds a mysterious and potent defense mechanism, tetrodotoxin, a venom that is as deadly as it is fascinating. This unassuming creature, often admired for its unique ability to inflate itself as a deterrent to predators, carries one of the most toxic substances found in the natural world. The venom of the pufferfish, primarily consisting of tetrodotoxin, TTX, is a potent neurotoxin known for its ability to block sodium channels on nerve cells, preventing the firing of action potentials. This blockade leads to paralysis and, in severe cases, death due to respiratory failure. The toxin is found not only in the glands of the pufferfish, but also in certain organs and the skin, serving as a powerful deterrent against predation. Tetrodotoxin, TTX. A neurotoxin that effectively blocks sodium channels, rendering nerve cells unable to communicate and muscle cells unable to contract. Additional components. While TTX is the primary component, the venom can also contain trace amounts of other compounds that may contribute to its overall toxicity and effects on the body. Tetrodotoxin acts by binding to the voltage-gated sodium channels in nerve and muscle tissue, preventing sodium ions from entering the cells and thereby stopping the electrical impulses that drive muscle contraction and nerve transmission. This action results in a state of paralysis that begins with numbness and tingling and can progress to severe and total paralysis, including the muscles necessary for breathing. The effects of pufferfish venom on humans are both rapid and dramatic. Symptoms typically begin with numbness around the mouth and lips, spreading to the face and extremities. This numbness soon gives way to increasing paralysis. In severe cases, this paralysis affects the diaphragm and intercostal muscles, leading to respiratory failure. Without immediate and effective medical intervention, the outcome can be fatal. The progression of symptoms underscores the potency of TTX, marking the pufferfish as one of the ocean's most subtle yet deadly inhabitants. The unique properties of tetrodotoxin have captured the interest of the scientific community, particularly in the field of pain management. Due to its ability to block nerve transmission without causing damage to nerve cells, TTX has potential as a powerful analgesic. Researchers are exploring its use in conditions characterized by severe pain, where conventional painkillers are ineffective. Additionally, the specificity of TTX in targeting sodium channels could lead to new treatments for channelopathies, disorders caused by dysfunctional ion channels. Lurking in the shadows at number 10 with a notorious reputation, the black widow spider possesses a venom that is as fascinating as it is feared. This creature, marked by the iconic red hourglass on its abdomen, injects a venom that is a marvel of biological engineering, reflecting a complexity that seems almost beyond the natural evolution of predatory tactics. The venom of the black widow spider is primarily composed of a neurotoxin known as latrotoxin, which targets the nervous system with precision and efficiency. This complex molecular structure forms the basis of the venom's potency, capable of causing significant physiological disruptions in mammals, including humans. What exactly are these toxins? Latrotoxin, the primary component that disrupts neurotransmitter release, leading to widespread neuromuscular and autonomic instability. Enzymes and peptides, supportive biochemical agents that facilitate the spread and increase the efficacy of the venom, intensifying pain and inflammation. When the black widow spider bites, it injects latrotoxin directly into its victim's bloodstream. The toxin swiftly binds to the presynaptic nerve terminals, particularly those controlling muscle contraction. Latrotoxin forms pores in the nerve cell membranes, causing an uncontrolled release of neurotransmitters like acetylcholine and norepinephrine. This flood of neurotransmitters leads to severe muscle spasms and pain, typical symptoms of a black widow bite. The specificity with which latrotoxin targets these nerve cells raises questions about the evolutionary origins of such a refined tool. How did such a specialized venom evolve? The answer lies perhaps in the intricate dance of predator-prey dynamics that has sculpted the spider's arsenal over millennia. The impact of black widow venom on humans is both immediate and painful. Initial symptoms include acute pain at the site of the bite, followed by muscle cramps, sweating, and nausea. As the venom spreads, systemic effects can manifest, including hypertension, severe abdominal pain, and muscle rigidity. The elderly and infirm may experience more severe neurological symptoms, such as convulsions or even respiratory failure due to diaphragmatic paralysis. The intensity and rapid onset of these symptoms underscore the venom's role as a potent defense mechanism and a highly effective means of subduing prey. Despite its potency, deaths from black widow bites are exceedingly rare, thanks to advances in medical treatment and the availability of antivenoms. The unique properties of latrotoxin have drawn significant interest from the scientific community, particularly in the field of neurological research. The toxin's ability to modulate neurotransmitter release makes it a valuable tool for studying synaptic transmission and potentially treating diseases characterized by neurotransmitter imbalances, such as Alzheimer's and Parkinson's diseases. Understanding the molecular structure of tetrodotoxin and its interaction with nerve cell membranes can lead to the development of novel pharmacological agents that can either mimic or inhibit its action. Such agents could be revolutionary in treating chronic pain conditions or in designing new types of anesthetics that provide pain relief without the side effects associated with current drugs. Amidst the quiet corners and undisturbed shelters at number 9, the Brown Recluse Spider, a creature as unassuming as it is dangerous, harbors a venom that belies its modest appearance. Known for its characteristic violin-shaped marking, this spider injects a venom that has puzzled and intrigued scientists due to its complex biochemical properties and the severe reactions it can provoke. The venom of the brown recluse spider is primarily composed of a variety of enzymes and proteins, each contributing to its potent effects. Among these, the most notable is sphingomyelinase D, an enzyme that stands out due to its ability to degrade sphingomyelin, a type of lipid found in cell membranes. This action leads to the destruction of cells and tissues, a hallmark of brown recluse venom. Sphingomyelinase D. This key enzyme directly attacks cell membranes, leading to necrosis, cell death, in the tissues surrounding the bite area. Hydrolyses and proteases. These enzymes further contribute to tissue damage by breaking down proteins and other cellular components, exacerbating the spread of necrosis. The mechanism by which the brown recluse spider's venom operates is both fascinating and horrifying. Upon being bitten, the victim's skin immediately begins to react to sphingomyelinase D. This enzyme disrupts the cell membranes by breaking down sphingomyelin, leading to the formation of lesions and ulcers. This process not only causes cell death, but also triggers an immune response that can lead to widespread inflammation and sometimes a systemic reaction known as loxoscelism. Loxoscelism, the condition caused by the venom, can manifest in two forms, cutaneous and systemic. The cutaneous form results in the death of tissues and skin around the bite site, often creating a characteristic ulcer that is slow to heal. The systemic form, though less common, is more severe and can affect internal organs, leading to symptoms such as fever, rashes, nausea, and in rare cases, hemolysis, destruction of red blood cells. The impact of brown recluse venom on humans can vary widely. While some individuals may experience only minor irritation and inflammation, others can develop severe dermatological and systemic symptoms. The venom's propensity to cause significant necrosis can lead to large, painful ulcers that require medical intervention to prevent infection and promote healing. In systemic cases, medical care becomes even more critical as the body's internal systems are under attack, posing a risk of serious health complications. The variability in symptoms and severity is a subject of ongoing research, with studies suggesting that individual immune responses and genetic factors may influence how one reacts to the venom. This complexity adds another layer of intrigue to the already mysterious nature of the brown recluse spider's venom. The unique properties of sphingomyelinase D have sparked interest in the pharmaceutical and biochemical research communities. Understanding how this enzyme interacts with cell membranes has implications for diseases characterized by similar mechanisms of cell damage, such as certain autoimmune and inflammatory disorders. The study of brown recluse venom is contributing to advances in dermatological treatments. Insights gained from how the venom induces tissue necrosis and inhibits healing are helping researchers develop better strategies for wound care and skin regeneration. The enzyme's specificity also holds potential for developing targeted therapies that can precisely modulate the immune system's response to tissue damage. At number 8, in the ethereal beauty of the coral reefs where the lionfish prowls, there lies a hidden danger as ancient as the seas themselves. The lionfish, with its flamboyant pectoral fins and bold stripes, carries a venom that is both a marvel of natural engineering and a significant ecological threat. The venom of the lionfish is a concoction of protein, each serving a specific function in subduing prey, focusing on pain management and the prevention of secondary infection. Immediate actions typically include immersing the wound in hot water to denature the proteins in the venom, thereby reducing pain and inflammation. The distinct properties of lionfish venom have garnered interest in the fields of neurology and pharmacology. Researchers are particularly focused on the neurotoxins, which have the potential to shed light on the fundamental workings of nerve cells and nerve muscle interactions. By studying these toxins, scientists hope to develop better treatments for chronic pain and other neurological disorders. The unique combination of cytotoxins and enzymes offers a new avenue for tissue damage. The enzymes in the venom, which facilitate toxin spread, might also inspire novel approaches in drug delivery systems, particularly in targeting cancer cells where precise delivery of drugs to the affected area can significantly improve treatment efficacy. Number 7 is lurking beneath the camouflage of its rocky appearance. The stonefish asserts its place as one of the ocean's most formidable inhabitants. Its venom, notorious for being the most potent of any fish, carries a legacy shrouded in mystery and pain. The venom of the stonefish is a sophisticated blend of proteins and enzymes designed to incapacitate its victims swiftly and effectively. Stored in glands at the base of the stonefish's dorsal fin spines, the venom is an intricate concoction that includes neurotoxins. These potent proteins disrupt nerve transmission, leading to severe pain and paralysis. Cardiotoxins. Targeting the heart, these toxins can cause fatal arrhythmias if enough venom enters the bloodstream. Myotoxins. Affecting muscle tissue, these toxins lead to muscle breakdown and necrosis, exacerbating the victim's physical suffering. Each component plays a critical role in the defense mechanism of the stonefish, contributing to a venom that is both feared and respected across the marine world. The venom is delivered through an efficient and ruthless method. The stonefish possesses 13 sharp dorsal spines, each connected to a venom sac. When pressure is applied to these spines, as when an unwary swimmer steps on the fish, the venom is forcibly ejected into the wound. This delivery system ensures that the venom is introduced deeply into the victim's tissues, where it can begin its devastating work quickly. Once injected, the neurotoxins in the venom rapidly impair nerve function, causing intense pain and immobilization. The cardiotoxins and myotoxins follow, disrupting heart function and breaking down muscle tissue, respectively. The combined effect of these toxins can lead to shock and, in severe cases, death if medical intervention is not promptly provided. The sting of a stonefish is one of the most painful wounds any human can endure. Victims often describe the pain as excruciating and immediate, with the affected area rapidly swelling and becoming grotesquely disfigured. The pain and swelling can spread, causing debilitating agony that, without treatment, can persist for weeks. Beyond the immediate pain, the venom can have systemic effects, including nausea, abdominal pain, fever, and chills. In cases where a significant amount of venom is absorbed, or if the victim suffers from an allergic reaction, the encounter with a stonefish can result in seizures, paralysis, heart failure, and even death. The intense potency of stonefish venom has made it a subject of intense interest in the field of medical research. Scientists are particularly focused on the neurotoxins and cardiotoxins for their potential applications in developing new pain management therapies and cardiovascular drugs. The neurotoxins offer a model for novel analgesics that could target specific nerve pathways, offering pain relief without the side effects of traditional narcotics. Similarly, the cardiotoxins may help in the creation of new treatments for arrhythmias and other heart conditions, providing a basis for drugs that can more effectively regulate heart function. Understanding how these toxins interact with cellular structures could advance our knowledge of cell biology, potentially leading to new insights into how cells repair themselves, how they communicate, and how they can be protected from or treated for various diseases. The notorious Africanized honey bee enters our countdown at number 6. Known colloquially as killer bees, these hybrids of the African honeybee and various European honeybees possess a venom that, while similar in composition to that of their more docile relatives, is delivered with a ferocity and persistence that elevates their threat. The venom of the Africanized honey bee has piqued the interest of the scientific community, not only for its immediate effects, but also for its potential applications in medical science. Researchers are particularly intrigued by melittin, the predominant component of bee venom, which has been shown to possess anti-inflammatory and antibacterial properties. Understanding how melittin and other components like apamin interact with human cells can lead to novel approaches in treating chronic pain and even diseases like arthritis and multiple sclerosis. The venom's complex mixture of enzymes, peptides, and amines offers a rich source for pharmacological studies aimed at harnessing these properties to develop new treatments. The venom of the Africanized honey bee is a complex mixture of various bioactive substances, each serving a unique role in the bee's defensive arsenal. The primary components include melittin. This peptide makes up about 50% of the venom's dry weight and is primarily responsible for the pain associated with bee stings. It acts as a powerful stimulator of the inflammatory response and can disrupt cellular membranes. Phospholipase A2, working synergistically with melittin. This enzyme enhances the lytic effects on cell membranes, contributing to the spread of venom through tissues. Hyaluronidase, often referred to as the spreading factor, this enzyme facilitates the diffusion of venom by breaking down hyaluronic acid in the connective tissue. Apamin. This neurotoxin blocks calcium-dependent potassium channels, which can affect cellular functions and contribute to pain and inflammation. The venom of the Africanized honey bee exerts its effects through a combination of mechanical and biochemical actions. When a bee stings, it leaves behind a barbed stinger that continues to pump venom into the victim. This venom contains substances like melittin, result in a more severe systemic reaction, including symptoms such as nausea, vomiting, fever, and in extreme cases, anaphylactic shock. This severe allergic reaction can lead to difficulty breathing, a dramatic drop in blood pressure, and potentially death if not promptly treated with epinephrine. Besides causing pain and inflammation, the venom of the Africanized honey bee also interacts with the human immune system in complex ways. By stimulating an intense immune response, the venom can lead to the release of histamine and other inflammatory mediators from mast cells, which not only increase pain perception, but also contribute to the swelling and redness seen at the sting site. This interaction between venom and immune response is critical for understanding how to treat and manage reactions to bee stings effectively. Each element of the venom, from the pain-inducing melittin to the tissue-spreading hyaluronidase, plays a crucial role in the bee's survival strategy while offering significant insights into human biology and medicine. As research progresses, the venom of the Africanized honey bee continues to be a subject of both caution and curiosity, holding secrets that may one day lead to breakthroughs in treating diseases that have eluded conventional medicine for decades. At number 5. Within the vibrant ecosystems of the world's coral reefs, where myriad forms converge in a symphony of color and life, the fire coral stands as a guardian of secrets old as the seas. Not a true coral, but a hydrozoan, the fire coral poses with a deceptive resemblance to its benign cousins. Yet it harbors a venomous mechanism, sophisticated and potent. Fire coral delivers its venom through microscopic nematocysts, which are spring-loaded cells unique to cnidarians. These cells, when triggered by contact, launch a harpoon-like structure that penetrates the skin and injects venom. The venom itself is a complex blend of proteins and peptides that act on multiple fronts. It disrupts cellular integrity, causes intense pain, and can trigger inflammatory and allergic reactions. The immediate effect of the venom is typically localized pain and swelling, but it can also lead to more severe systemic reactions depending on the extent of exposure and individual sensitivities. The study of fire coral venom is relatively nascent but holds promising avenues for medical research, particularly in understanding how its components interact with human tissue. Researchers are interested in isolating specific toxins within the venom that have the potential to modulate pain pathways or immune responses. These components could lead to the development of novel pharmaceuticals aimed at treating chronic pain or autoimmune disorders, offering new hope where traditional medications have failed. The venom of fire coral contains a variety of compounds, including neurotoxins that affect nerve cell function and cytotoxins that damage tissue. These substances are designed to incapacitate small prey and deter predators, playing a critical role in the survival and feeding strategies of fire coral. Among the venom's myriad components, researchers have identified neurotoxins. These disrupt neural transmission, leading to pain and potential paralysis. Cytotoxins. They attack cell membranes, causing cell death and tissue degradation at the contact site. Enzymes. These facilitate the spread of toxins by breaking down host tissues, enhancing the overall venom efficacy. The interaction of fire coral venom with human skin typically results in what is commonly referred to as fire coral burns, which are painful and can be surprisingly severe. The affected area becomes red and swollen, and the pain can be accompanied by nausea and vomiting if the exposure is extensive. In cases where the venom spreads systemically, it can cause symptoms such as fever, chills, and in rare cases, shock. Immediate first aid, including the careful removal of tentacles and application of vinegar to neutralize nematocysts, is crucial to mitigate the effects. As research into fire coral venom advances, there is increasing interest in the potential applications of its unique properties. The complex mix of toxins that make up the venom is being studied not only for its direct effects, but also for its potential to inspire biomimetic technologies in materials science. For example, the mechanisms by which nematocysts deploy could inform the development of new delivery systems for drugs, allowing precise targeting of diseased tissues without affecting healthy cells. The venom's ability to manipulate pain and immune response at the molecular level is of particular interest to neurologists and immunologists. By studying how the venom's neurotoxins and cytotoxins interact with human nerve cells and immune cells, scientists hope to gain insights into managing pain and autoimmune diseases, potentially leading to breakthroughs in how these conditions are treated. Each strand of inquiry into the fire coral's venom weaves a narrative of biological ingenuity and adaptability. With its potent defensive mechanisms and complex chemical makeup, fire coral not only captivates those who study the natural world, but also holds keys to unlocking new scientific and medical paradigms. As we continue to explore the venom's properties and applications, the fire coral remains a testament to the intricate connections between marine life and human health, highlighting the profound influence of nature's designs on modern science and medicine. In the shadowed crevices at number 4, beneath the stones of South Asia, lurks the Indian red scorpion, one of the most dangerous scorpions in the world. Its venom, a complex biochemical toolkit, strikes an intricate balance between lethality and precision. This exploration delves into the venom of the Indian red scorpion, investigating its composition, the detailed mechanisms of its action, and the broader implications for medical research. The venom of the Indian red scorpion is primarily neurotoxic, targeting the nervous system of its victims with devastating efficiency. It contains a mix of toxins that enhance the release of neurotransmitters at nerve endings, leading to uncontrolled neuronal firing. This barrage of impulses results in severe pain, muscle spasms, and potentially life-threatening disruptions in heart and respiratory function. The venom achieves this through a potent cocktail of peptides and proteins that alter ion channel activities, particularly those that regulate sodium and potassium levels across nerve cell membranes. The sting of the Indian red scorpion is notoriously painful and can be deadly, particularly in children. Symptoms following envenomation are severe, including pain at the sting site, vomiting, sweating, salivation, and a dramatic rise in heart rate and blood pressure. In severe cases, the venom can lead to pulmonary edema, a buildup of fluid in the lungs that can cause respiratory distress and, if untreated, death. The severity of the reaction is influenced by the amount of venom injected and the physiological response of the victim. Research into the venom of the Indian red scorpion has opened up promising avenues in medical science, particularly in the areas of cardiovascular and neurological disorders. The venom's ability to manipulate ion channels offers valuable insights into the development of drugs that can regulate heart rhythms or control epileptic seizures. Furthermore, because the venom components target specific pathways in nerve cell function, they can be used as tools to map the complex processes of nerve transmission, offering potential breakthroughs in understanding and treating nerve-related diseases. Beyond its immediate medical applications, the venom of the Indian red scorpion is also being studied for its potential as a natural pesticide. Its ability to disrupt neurological systems without harming crops makes it an attractive alternative to chemical pesticides, which can be detrimental to the environment. This application not only highlights the venom's versatility, but also underscores the potential for bio-based solutions in agricultural practices, fostering a more sustainable approach to pest control. The venom of the Indian red scorpion, Hottentotta tamulus, is rich in a variety of compounds that together create a potent biological weapon. These include neurotoxins. These are the primary active components that disrupt the normal functioning of nerve cells, leading to severe neurological symptoms. Cytotoxins. Although less prominent, these toxins affect cellular integrity and contribute to the local and systemic reactions observed following a sting. Enzymes. These facilitate the spread of the venom through the victim's body, increasing the efficiency and speed of the toxic effects. The venom's impact on pain perception is profound. It triggers an immediate, intense pain response at the site of the sting, which serves as a deterrent against predators. The immune response to the venom can also be significant, with the body recognizing the venom proteins as foreign invaders and mounting a defensive reaction. This immune response can sometimes exacerbate the symptoms of envenomation, leading to complications like swelling, redness, and increased pain. The study of the Indian red scorpion's venom offers key insights into human physiology, particularly how our bodies manage pain and react under acute stress. The venom's specific targeting of ion channels and neurotransmitter release mechanisms provides a unique framework to study these processes under extreme conditions, offering clues that could lead to more effective treatments for chronic pain and other stress-related disorders. At number 3. Deep within the lush canopies of sub-Saharan Africa, the boomslang lurks with a deadly grace, its presence barely noticed until it strikes. This arboreal serpent, whose name translates to tree snake in Afrikaans, wields a venom that is both fascinating and terrifying in its biological sophistication. The venom of the boomslang is primarily a hematoxin, which exerts its effects on the human vascular and clotting systems. Unlike neurotoxic venoms that attack the nervous system, hematoxins such as those found in boomslang venom dramatically affect blood cells and blood vessel walls, leading to severe hemorrhaging throughout the body. The venom contains enzymes that degrade the structural components of blood vessels, causing them to become exceedingly fragile and prone to rupture. Furthermore, it disrupts the clotting cascade, preventing blood from clotting efficiently, which can lead to uncontrollable bleeding, even from minor cuts or bruises. The venom of the boomslang contains a variety of compounds, each contributing to its deadly efficacy. Proteases. These enzymes break down proteins and peptides, which are crucial for the structural integrity of blood vessels and for the clotting process. Phospholipases. These enzymes disrupt the phospholipids in cell membranes, further contributing to cellular damage and vascular leakage. Metalloproteinases. Involved in the degradation of collagen and other extracellular matrix components, these enzymes facilitate the spread of venom through tissue spaces. The effects of boomslang venom on humans are particularly severe due to its potent hemorrhagic properties. Initial symptoms might be misleadingly mild, including headache, nausea, and a general sense of malaise, which can delay effective medical response. However, as the venom spreads, more dramatic symptoms manifest, such as severe internal and external bleeding, blood in urine and stools, and progressive deterioration of organ functions. Without anti-venom, the mortality rate from a boomslang bite is high, underscoring the need for immediate medical treatment. The unique properties of boomslang venom make it an area of intense interest for scientific and medical research. The hemorrhagic effects of the venom are studied not only for better understanding and treatment of envenomation, but also for their implications in treating human conditions that involve excessive clotting and other blood disorders. The enzymes within the venom, particularly the metalloproteinases and phospholipases, are of great interest for developing new drugs that can alter blood properties in diseases where clotting is a factor, such as heart attacks and strokes. Researchers are exploring the therapeutic potentials of boomslang venom in various medical fields. By studying how the venom's components interact with human blood and vascular tissues, scientists hope to develop novel treatments for conditions that currently lack effective therapies. For example, the anticoagulant properties of the venom might be harnessed to create new blood thinners that are more controllable and with fewer side effects than those currently on the market. Interestingly, despite its lethal nature,